Hey, I'm Benny Seidman, an alumni of the South Eugene IB Physics program, and currently an admitted student at a stuffy New England college.
Hello everybody, my name is Lucy L. Goldenberg. I am also an alumni from South Eugene Physics program, and I'm going to an incredibly prestigious school with an incredibly low, subjectively low acceptance rate of 80%, and I will be majoring in physics. Thank you. Hello everyone, and thank you so much for joining us with our Docu-lecture today. During this Docu-lecture, we are going to be explaining very important topics, including but not limited to
Relativity, the Doppler effect, and Cepheid variables.
And also how these pertain to astronomy and why these matter at all.
Thank you for joining us.
Thank you. Throughout this documentary, me and Benjamin Seidman are going to go into detail about the two ways that, well, there are many other ways, but we are going to go into two ways about how we can measure distances to the stars, using Cepheid variables and using the relativistic Doppler effect and spectroscopy. Thank you.
All right, for the purposes of our documentary, we're going to use the Cepheid variable for the Adena star 2443 of the Malahim galaxy. All right, so Mr. Einstein, would you care to tell us a little bit about what you've advanced in the field of physics?
Yes, thank you. I have done an incredible amount of advancement in the field of physics. One of the most notable, which I think you will be talking about today, is that of special relativity. The idea, I cannot summarize this idea in one sentence, but it is an incredible idea, and it was my discovery. Thank you.
You're welcome. All right, so Galilean relativity is the most simplistic version of relativity. It assumes that length and time are unchanging depending on the observer. And in actuality, this is an oversimplification. However, at low speeds, far less than the speed of light, it is approximately right. And you can add or subtract velocities to find relative velocities. But this can't work.
What? Oh my god.
No! You cannot keep that in.
Unfortunately, due to the constant nature of the speed of light from all points of reference, from all perspectives, length and time are not actually conserved from all perspectives. This leads to length contractions and time dilation in different circumstances as different observers approach the speed of light relative to one another. Alright, because velocity equals distance over time and the speed of light is constant, time dilation occurs as one observer approaches the speed of light. So, when one observer is going a significant proportion of the speed of light, this observer will measure the proper time, or the time in their frame of reference. Every other frame of reference in which they are moving relative to that frame of reference will measure a slightly dilated or longer time. This happens in the opposite way for lengths, with the proper length being measured by that same observer, but every other length measured in a different frame of reference showing the same length to be slightly smaller or contracted.
By a factor of what, Benny?
Gamma.
What's gamma?
Gamma is equivalent to 1 over root 1 minus v squared over c squared.
That's amazing. Thank you. Hello, who am I here with today?
Grace, Lily.
And I have a little story for you, Grace and Lily. So, this is just a hypothetical, but let's say that I ran around you two. If you were sitting on the highway right there, stationary compared to what we are now, and if I ran around you guys for a year straight, going at how many? Let's say 5 miles an hour. 5 miles an hour for a year straight, and you guys just stayed there. Did you know that it would actually it would be a little tiny bit less than a year for me. I would observe time a little bit differently than you guys. You guys would say, oh yeah, that was absolutely 1 year. And I might say, no, it was 0.99997 of a year. Did you guys know that?
I'd be impressed by your skill to calculate how long a year is.
Did you know that, Lily?
I think your perspective is wrong.
Why do you think my perspective is wrong?
Because it is what it is.
Lily thinks it is what it is. What do you think is what is?
If it was a year, then it was a year.
Well, let me just tell you that even though it's crazy, is actually wrong because of special relativity. Because light, nothing can go faster than the speed of light, and that has incredible consequences. How do you feel about that? You know, like that was just one kind of possibility. My shoes just fell off. That was just one that rocked my world. That rocked her world. What about you?
That was a pretty spectacular answer.
Thank you so much. Thank you guys.
All right, so did you know that the very bus we are on right now is slightly shorter by a matter of about 1 atom of paint from the observer who is stationary relative to the motion of our bus? And how do you feel about that?
Sorry, what?
All right, this bus is shorter
Okay.
from the stationary perspective outside than it is from our perspective within the bus.
Okay.
Is that not trippy as heck?
It's literally trippy as heck. I took everything if you not to say widowy. Oh wait, shit, you're still feeling.
heck.
It is a widowy twippy as heck right now.
Another consequence of Einstein's special theory of relativity is that of the relativistic Doppler effect. The relativistic Doppler effect is very cool because things can be observed as if they changed colors, such as a star in a distant galaxy. If it's going super fast, it will be either blue shifted or red shifted. If it's going away from our galaxy, it'll be red shifted. If it's going towards our galaxy, it'll be blue shifted. And this happens. Why does this happen? This happens because it's kind of the same, you guys know the Doppler effect. It's the same principle just with light. And because light doesn't change speed, the frequency and the wavelength have to change. And the wavelength, now what does that control? The wavelength controls color. So if the frequency is getting shorter, the wavelength will be getting longer. Yeah, the wavelength will be getting longer, and therefore redshift or bluer. The wavelength will be getting different, either bluer or redder, and that's how it works. Hello again. So, how can we use the relativistic Doppler effect to find the distances to really fast stars? Now, these stars that we're measuring are going to be very distant and therefore are going to be affected by something we call the Hubble law of expansion in the universe. And that basically is just the universe is expanding at an accelerated rate, and as you go further and further away from where you are, we are on Earth, therefore as you go further and further away from Earth, everything's going to be expanding faster and faster, and that's actually going to be in a directly correlated graph. So then as the farther you go, it's going to be faster, so it's just a linear graph. And basically, once this applies to spectroscopy because we can look at the elements in these stars really far away, and we're going to see a spectrograph of the elements such as hydrogen and they're going to be shifted either, well, in this case, they're usually going to be shifted, redshifted, because they're so far away. So they're going away from us really, really fast. And because of the relativistic Doppler effect, they're going to be redshifted, and therefore we can use how much it's shifted to actually measure how fast it's going. And then once we measure how fast it's going, boom, we've got the distance.
All right, so this is a demonstration of the Doppler effect as demonstrated by Limp, who represents the star. As the star moves away from us, as you can see, it is redshifted because the wavelength of light that it emits becomes more spread out as it's received by us. This shows blue shifting as the same star approaches us because the wavelength of light received is now contracted. There's less time between successive light waves.
This is the calculation of the distance of star Adena 2443 part of the Milky Galaxy using the relativistic Doppler effect in spectroscopy. So for the observed wavelength, it is 5.181 times 10 to the 7th meters. For the predicted wavelength, it is 5.173 times 10 to the negative 7th meters. So then we plug that into the equation we got from deriving a bunch of the relativistic Doppler effect equations from our the special relativity equations. And so we plug those numbers in, and for the speed we get 4.636 times 10 to the 5th meters per second, and so that's the speed of Adena. And then from there we used the Hubble's law equation, which is just velocity equals the Hubble's constant times distance. And we plug the numbers in for distance equals velocity over Hubble's constant, and from there we got 6.614 megaparsecs is the distance to Adena.
Hello, everyone. I'm here with Henrietta Levitt. Henrietta Levitt, can you please tell us a little bit about yourself?
Yeah, so my name's Henrietta Levitt. I don't know what I did.
Henrietta Levitt, what did you discover?
I discovered the Cepheid.
My bad. She discovered Cepheid variables.
Cepheid variables, that's right. Pulsating stars.
And we'll talk a little bit about those later, but she made an incredible discovery and really progressed the women in STEM movement a few hundred, maybe less than 100 years ago.
Yeah, right.
Thank you for coming on the show.
Did you know that we can measure the distance to distant Cepheid stars, which pulsate, just by measuring the differences in their luminosity?
How do you do that?
Why don't we just ask Henrietta Levitt?
Oh my God, did you just see that? Was that a pulsating star? Its brightness has changed over the course of a few days in a recognizable pattern. What could this mean? I just realized something. We can measure, first we measure the period of fluxation, brightnessation, the period of the way it changes in flux, brightness. And then once we do that, we can actually measure how bright the average brightness is, as if we were standing right next to the star. That's the real luminosity. Now, we can also measure the brightness that is apparent to us, the brightness that we get from the star here on Earth. And using these two brightnesses, what can we find? We can find distance. Now, we just found the distance to this beautiful pulsating Cepheid. Okay, stop it.
This is the calculation of the distance to Adena 2443 from the Milky Galaxy using the Cepheid variable method. And for this hypothetical star, the period is 9.3 days, and the average magnitude of the star is 52.16. So we got this very long equation from deriving a bunch of equations for Cepheid variables and distance correlated to brightness and luminosity. And then we plugged those numbers into this really long equation, and we got the distances 2.460 times 10 to the 23rd meters, oh my God, which is approximately 7.972 megaparsecs. So this is the distance to Adena 2443, as seen by the Cepheid variable method.
Hello, I'm here with
Relativistic.
Pearl, we've been talking a bunch about these two methods of finding the distance to these stars, and I just wanted to ask you, which method do you prefer, the Cepheid variable method or the redshift method?
I like the redshift method. I think it's a little more accurate, more diverse, and it lets you know like the velocity of things.
Yeah.
Stars.
Thank you so much, Pearl.
Thank you.
Have a good day. Yeah. Hello, who am I here with today?
Madeline.
Hello, Madeline. After going through both those two methods with everyone on this bus, we wanted to interview everyone on what do you think is the better method? Which one do you prefer to do, or what do you just like better?
I like the relativistic Doppler effect because I like all the colors.
That is a great reason. Thank you so much, Madeline.
All right, we're here with Lila from PBYO, of course. And why do you feel that astronomy is important in our society today?
I think that astronomy is important so that we can eventually learn if there are species on other planets and compare how they survive and how they live to us on Earth.
Awesome. Thank you, Lila.
Hello, could you tell me who I am here with today?
My name is Gemma Pete.
Okay, hello, Gemma Pete. We have a question for you today. Why do you think astronomy is important?
I think astronomy is super important so we can have stars in the sky and we always know where we're going when we follow the North Star. And if you get lost in the ocean, you can always find your way.
Thank you so much, Mrs. Pete. It was great talking to you today. Thank you.
Thank you so much for joining us once again for our docu-lecture here. I'm Benny Seidman. I will be attending Stuffy New England College this coming fall.
And I am Lucy, and I will be attending the best college in the world, CU Boulder. Thank you all so much for watching. Goodbye.
Reach for the stars, guys.
Reach for the goddamn stars. Okay. We are going to be talking about a variety of topics, including, but not limited to,
The Doppler effect. What the fuck? That I messed up. We got to retake.
Wait, am I in it?
could pan a little quicker.
Okay, so,
Hey everyone, I am an honorary member of the documentary. I just want to say that velocity equals time over mass.